Our final problem is a number 12, pretty difficult, from the 2021 AIME I. Let A1, A2, A3, and so on to A12 be a dodecagon. 3 frogs initially sit at A4, A8, and A12. So let's draw that. So we have 12 points. Now I'll just draw them along a circle, though it says dodecagon. It's the same idea. 12 points, equally spaced, and they sit at A4, A8, and A12. Let's just use the standard clock numbering here, right? So that we have 3 frogs basically evenly spaced along this. So 3, basically 1 here, 1 here, and 1 here. 1, 2, and 3. Now, at the end of each minute, simultaneously, each of the 3 frogs jumps to one of the 2 vertices adjacent to its current position, chosen randomly and independent, with both choices being equally likely. So, for example, A12 can jump to either A11 or A1. All 3 frogs stop jumping as soon as 2 frogs arrive at the same vertex at the same time. The expected number of minutes until the frogs stop jumping is m over n, where m and n are relatively prime positive integers. Find m plus n. So let's take a look at our starting configuration and just think about all the possibilities. Since there are 2 choices for each frog to jump, there are 2 times 2 times 2, or 8 different configurations we could end up with after all the frogs have jumped at the end of the first minute. One such configuration, imagine every frog jumps clockwise, so that now they lie on these 3 points here. Right, so let's take a look at this. A1, A5, and A9. Notice how the configuration has basically just rotated by 1, right? So we can see that actually this does not change the expected number of minutes until the frogs stop jumping. We just basically use a move, and now the expected value stays the same. So let's think about all possibilities here. Let's consider 2 frogs at a time. Imagine you have 2 frogs here, and just consider all 4 possibilities, right? Well, they could jump towards each other, right? Both of them moving inwards, which reduces the distance between them by 2. They could move away from each other, which will increase the distance between them by 2. Or they can move in the same direction, either both clockwise or both counterclockwise, both of which produces no net change in the distance between the 2 frogs. So basically, notice that this has basically a 1/4 chance of happening. These both have 1/4, and this has 1/2 chance happening. So we can see that the distance between any pair of frogs, right, let's just use clockwise distance, will always change by either 2, -2, or 0, right? And notice how it starts at 4, so each of the 3 frogs are 4 away from each other. So we can see that we can basically encode this configuration as basically the distance between each pair of frogs, right? So there's 4, 4, and 4 as the first one. And notice that since they only change by 2s, we can actually just divide this whole thing by 2, because we're only changing by an even number. So really, we can encode the initial condition to be 2, 2, and 2, right? Where 2 represents a distance of 2 times 2, or 4, between the 2 frogs. And so we have something like this, right? And so we can see that in the case where every frog moves in the same direction, there is no net change in any of the distances. So we can see that, for example, if everyone moves clockwise, then 2, 2, 2 still goes to 2, 2, 2. But imagine that instead of everyone going the same direction, we can have one of them moving in an opposite direction, right? Either all of them move in the same direction, or 2 frogs move in the same direction, and another one moves in the opposite direction. In this case, the distance is changed by 0, plus 2, which will represent as a plus, and -2 on the bottom there, right? So you can see that the distance go from 4, 4, 4 to now the distances go to 4 here. The distance here is now 2 after having decreased by 2, and this one has expanded by 2. So the total distance is still 12 around the circle, but we can see that it's been redistributed. In particular, we have a 0, a minus, right? Minus meaning minus 2, and a plus. So this configuration goes to 4 becomes 2, 1, and 3 under the encoding, right? Where each gap of 2 represents 1. So you see that 2, 1, 3, this goes to 2, 1, 3, so that the distances are 4, 2, and 6. So you can see whenever two of the frogs move in one direction and the other moves in the opposite direction, then one of the distances does not change. One of them increases by 2, and the last one decreases by 2. So if we consider all of the possible ways the frogs can move, there are two choices where none of the distances change, basically everyone moving either clockwise or counterclockwise. So that keeps the thing the same, the configuration, that code. Otherwise, right, there are basically 6 other combinations of moves where 2 of the frogs move one way and the last frog moves the other way, which produces 1 increased distance, 1 equal distance, and 1 decreased distance. So we can summarize our results like this. Let's create a table first. So in 2 of the cases, none of the distances change, right? So this is, we can represent the change as basically this triple of numbers, right? 0, 0, 0 means none of the distances change. We can have, if we move all in the opposite direction, it's 0, 0, 0 still. And then we can represent the other cases like this, right? Minus 0 plus, meaning the distance between frog 1 and frog 2 decreases by 2. The distance between 2 and 3 stays the same. And the distance between 3 and 1 increases by 2, right? And you can see that there are 6 permutations. And all in all, we have 8 total possibilities, which corresponds to the 8 possible ways for the frogs to jump, right? So these are all 8 possible changes. And we can see that the initial the initial state is 2, 2, 2, with all of the frogs being distance 4 from each other. And you can see that we can apply these changes so that, right, the distances stay 2, 2, 2 in these first 2. In this one, it decreases by 1. It stays the same, and this increases by 1. And you can repeat this for all of them, right? And actually, when we fill this out, one thing to notice is that everything other than the 2, 2, 2, where nothing changes, is some permutation of 2, 3, 1, right? Because of that symmetry. So we can see that we have 2 cases where it stays in the original state, just rotated either clockwise or counterclockwise. And the other ones are permutations of 1, 2, 3, in which the distances are 2, 4, and 6 in some order. Now, we can see that we now have a new state, right? We can just list out all possible states before termination, and we'll see what happens, right? Now that we have this, we can see that we can apply the exact same idea, right? 1, 2, 3, 1, 2, 3, just like normal. Minus 0 plus becomes 0 to 4. Notice that whenever we hit a 0 in any of these, that means the distance between 2 frogs is 0, which means that this represents a termination, right, state, where basically we end the sequence and see how many moves we've totaled. And you can see that this will be similar here. We have 0, 3, 3, so that will also end. We have 1, 1, 4 here. We have 1, 3, 2. We have 2, 1, 3. And finally 2, 2, 2. So you can see in 2 of these sequences, there's a 0, so those result in termination. We can see that 4 of these sequences turn back into 1, 2, 3 in some order. Or by symmetry, the expected number of moves from any of these permutations should always be the same, right? It should not depend on the order of these numbers because of the symmetry of the problem. And we also have this 2, 2, 2, which we encountered before. And then finally, this new state where we have 1, 1, 4, in which the distances are 2, 2, and 8 in some order. So we can, and this is actually the only other case where all the three numbers add up to 6 and all the numbers are non-zero. So you can see that in this case, the majority of these actually go to the termination, right? If either of the ones becomes a 0, in other words, if there's a minus in the first two spots, then we immediately end, right? We can see that 1, 1, 4 goes to 1, 1, 4 in the first two cases. Minus 0 plus will yield 0, 1, 5. Minus plus 0 is 0, 2, 4. 0 minus plus is 1, 0, 5. This one is going to be 1, 2, 3. This one's going to be 2, 0, 4. And finally, 2, 1, 3. So you can see that in this case, 4 out of the 8 result in termination. Okay. So now with all of this, we can assemble a table, basically a state diagram that shows all possible paths from the initial. So let's call these three states A, B, and C, and we can write equations representing the expected value from each of these states to termination. Right, so we can start at 2, 2, 2. Notice that 2, 2, 2 has a 1/4 chance to go to itself, and a 3/4 chance to go to 1, 2, 3 in some order, all of which have the same expected value. So this gives a probability of 3/4 going here. 1, 2, 3 has a 1/2 chance, right? These four cases where it goes to itself. A 1/4 chance, these two cases here, where it goes to the end state, right, where there's a 0. And finally, an additional, let's see, there's a 1/8 chance that it goes back to 2, 2, 2. And there's a 1/8 chance that it goes to 1, 1, 4. And then finally, if we're at 1, 1, 4, then there is a 1/4 probability of going to itself. So those are those two cases. There's a 1/2 chance of immediate termination. And then finally, 2 of the cases, so 2 out of 8 or 1/4 of the cases go back to 1, 2, 3. This is actually enough to solve for the expected number of steps from A, B, and C to termination. Right? Let's take a look at how we can construct each of these equations. For example, let E sub A be the number of steps that we need from A to termination on average, right? The expected number, E sub A. Well, we can write that as, well, there's a 1/4 chance that we make a step and we end up back at EA. So we can see that in this case, nothing has changed except we've expended one extra move. So in this case, there's a 1/4 chance that the total number of moves expended is just 1 plus the number of moves after the first, which is just, well, if nothing's changed, then the expected value is still E sub A. Similarly, there's a 3/4 chance that we spend a move and then we end up in situation B, after which there will be on average E sub B moves to go. So you can see that in this case, the total would be 1 plus E sub B on average, and there are no other cases. We can simplify this to be, if we just distribute it out, we can get that this is 1, right, taking out the 1/4 times 1 and 3/4 times 1, plus 1/4 EA plus 3/4 EB. And we can write the same for EB and EC using the similar ideas, right? EB is going to be, well, there's a 1/8 chance of going to EA again, so that's that, plus 1/2 chance of going to itself, and finally a 1/8 chance of going to EC, and finally there's a 1/4 chance that it just immediately ends, so that's a total of 1 move. And once again, if we take out those 1s, we just end up with 1/8 plus 1/2 plus 1/8, 1/4. Since those probabilities add up to 1 always, we know that we have a 1 at the start and then a 1/8 EA plus 1/2 EB plus 1/8 EC. Finally, we can write EC using the same idea as 1 plus, and then there is a 1/4 chance of going to B, And then there's also a 1/2 chance, or 1/4 chance of going to itself. And then, of course, there's a 1/2 chance of going to itself. Though that 1 will basically factor into this one here, right? If we wrote it out, it would just expand to this. So now we have these 3 equations, 3 unknowns, 3 equations. We know we're probably going to have a unique solution, and we do. If we solve this out, we actually get E sub A equals 16/3, E sub B equals 4, and E sub C equals 8/3. We can verify that this will satisfy all of the equations. So we end up with the final answer of, well, in this case, since it's asking for the expected number of minutes until the frogs stop jumping from the initial condition of 2, 2, 2, that expected value is 16/3. And since it's asking find m plus n, our answer is just 16 plus 3, or 19.